Now we're going to discuss slant or oblique asymptotes. So a slant or oblique asymptote occurs when the degree of the numerator is 1 degree greater than the degree of the denominator. We should remember that from previous lessons, but if not, I would highlight that and keep note of it. It has to be exactly 1 degree greater in the numerator than denominator. The slant asymptote is the quotient polynomial found by using long division. So let's recall the long division algorithm both numerically and algebraically. So the division algorithm, if f of x and g of x are polynomial functions, g of x cannot be 0. Then there are unique polynomials q of x and r of x. So you can't have 0 in the denominator here or else it's undefined. That's what that's saying. Okay? So let's take a look here. So numeric long division, this is what you guys did way back in the day. Okay, even what I did. So we have 675 divided by 21. Okay? 21 cannot go into 6, but it can go into 67. How many times can 21 go into 67? Most it can go in is about 3 times. Okay? And 21 times 3 is 63. When I subtract that, 67 minus 63 is 4, and then you bring down the 5. How many times does 21 go into 45 now? Most it can go in is 2 times, because 21 times 2 is 42. Subtract that from 45, and we end up with 3. There is no other number to bring down, so 3 is my remainder. The quotient is what was left over up top right here, so 32. Okay, so the way you would write your answer, let me make that a little easier to read there, would be 32 and 3 over 21, because I'm doing 3 divided by 21 still, but I can't do that. Okay, 3 over 21 does reduce though to 1 over 7, so that would be the most simplified form there. Okay? Now polynomial long division. I do feel that you guys are getting better at this. So again, this is kind of just like a review, but we have 6x squared plus 7x plus 5 all being divided by 2x plus 1. Now remember, if you're missing any terms, you need to plug in zeros from the highest to lowest degree, but I'm not missing any terms, so I'm good there. Or from the highest to lowest exponent, my apologies. Okay, so 2x times what gives you 6x to the second? Let's see, that would be 3x. So 3x times 2x is 6x squared, which is what I want. And 3x times 1 is 3x. Okay, then I'm going to subtract these terms, so that changes the signs. Those cancel. 7x minus 3x is 4x. And bring down the 5. Okay. Now, let's see. 2x times what gives you 4x? That'd be 2. Positive 2, so that's plus 2 right there. 2x times 2 is 4x. And 2 times 1 is 2. All right. I'm going to subtract those terms. That changes my signs. The 4x's cancel, and 5 minus 2 is 3. There's nothing else for me to bring down. So notice 3 is my remainder. Hey, that's what happened over here, okay? And my quotient is 3x plus 2. I don't know if you guys noticed, but these problems are very similar. The 6, 7, 5, and the 21, the 2, 1, okay? And notice you get 3x plus 2, and your remainder was 3. Okay, so that's how these problems are like kind of similar. So your answer for this would be 3x plus 2 plus, because it was a positive 3, 3 over the 2x plus 1, because that's what we divided by. And it would look like that. Okay. Okay, so that's just polynomial long division. That's not my actual slant asymptote. Remember, the slant asymptote is just what's left over right there. Okay? All right, so let's look at example 6 real quick. And it says, let g of x be x to the third plus 3x squared minus 10x over x squared plus 8x plus 15. Find the equations for your asymptotes of the graph g of x. So I am going to rewrite this in factored form. So let's see, I have a GCF of x in the numerator. So x squared plus 3x minus 10. I can factor out that denominator. Let's see, 5 and 3, both positive. So that's the factored form. It looks like I might be able to factor that numerator some more, so let's do that. Um, 5 and 2 plus 5 minus 2. That looks good to me. My x plus 5's go away. So I end up with x over x minus 2. Got a little wonky there. And then x plus 3 in the denominator. Okay. Alright, so that's the g of x function simplified in factored form. So I have a vertical asymptote at x equals -3. And I set that denominator down here equal to 0. I have a horizontal asymptote by looking up here at these. The numerator degree is greater than the denominator degree, so I actually do not have a horizontal asymptote. Okay, because remember, you're comparing x to the third is greater than x squared, so that means no horizontal asymptote. And then my slant asymptote, because the degree of the numerator is exactly 1 degree greater than the denominator, I do have a slant asymptote, and I can find that using, I'm gonna have to use long division. I can't do synthetic division because this is not a linear function. All right, so one thing though that you guys can do is you can do polynomial long division with this, with the simplified form, or synthetic division because this is linear here with this simplified function, okay? But notice that this is really x squared minus 2x plus 0 because you would need to include that missing term, the constant, and in the denominator you have x plus 3. Okay, so just be aware of that. That 0 right there. I am going to do long division just because we did that there as well. So I would have x plus 3 right there, and I would put the x squared minus 2x plus 0 right there. Okay, and then I would say x times x gives me x squared, and x times 3 is 3x. When I subtract those cancel, and I end up with negative 5x. Bring down the 0. And I'm going to multiply this x by negative 5 to get negative 5x. And negative 5 times 3 is negative 15. These both become positive when we subtract them. So I end up with 15 as my remainder, and you can ignore that. So my slant asymptote is x minus 5. Okay, if you want to do the synthetic division, remember you would do, set that equal to 0, so it would be negative 3, and then you write the coefficient, so 1, negative 2, 0. Bring down the 1. 3 times negative 1 is negative 3. Negative 2 minus 3 is negative 5. Negative 5 times negative 3 is 15. Add those, 15 is your remainder. This was x squared, so this becomes your x term. That's your constant, that's your remainder. That's what you have right there. So either one works, or you can do polynomial long division with the original setup. Up to you. Number 7. Here, sorry. All right, we are going to determine if the following rational functions have a horizontal asymptote, a slant asymptote, or neither. And if the function has a horizontal asymptote, I want you to write the equation of that asymptote. So looking at example 1 right here, the degree of the numerator is 1, the degree of this denominator is 2. So when I do x to the first, that is less than x to the second, which means I have a horizontal asymptote at y equals 0. That's the case every time the degree of the denominator is greater than the degree of the numerator. The horizontal asymptote's at y equals 0. So that would mean I do not have a slant asymptote. Okay, and it looks like, yeah, we're just finding horizontal and slant. All right, letter B. I have a degree of 2 and 2. So because they're equal, we divide the leading coefficients. So because x squared equals x squared, I am going to do 5x squared over 2x squared, which equals 5 over 2. So y equals 5 over 2 as my horizontal asymptote. Letter C. My degree is 2, and this, the degree of the denominator is 1. So because x squared is greater than x to the first, that means I have no horizontal asymptote. But because the degree of the numerator is exactly 1 degree greater than the denominator, I will have a slant asymptote. So I am going to do polynomial long division to find that here. So I have 4x squared plus 0x minus 8 all over 2x plus 1. I'm going to divide that by 2x plus 1. Pay attention, I did put a 0x right here because I start with x squared and I don't have an x term, so that's why I plugged in a 0 there. So you gotta pay attention to that guy. All right, so let's see here. I'm going to multiply by 2x to get 4x squared. 2x times 1 is 2x. And let's subtract those. So I get negative 2x, bring down the minus 8. Looks like I just need to multiply by negative 1 now. So negative 1 times 2x is negative 2x. Negative 1 times 1 is negative 1. Those both become pluses. So that's negative 7 is my remainder. And I don't really care about that remainder because my slant asymptote is at y equals 2x minus 1. It's whatever is left over up there. Hopefully we are getting the hang of this by now. Okay? All right, and then letter D. Notice that there is no x term in this numerator. So that means that we have x to the 0 because anything to the 0 power always equals 1. Okay? So I'm comparing x to the 0 and x squared. X to the 0 is obviously less than x squared. So I have a horizontal asymptote at y equals 0. Okay? Sorry, I just want to make sure I check something real quick. Okay, I'm good. All right. All right. And then number 8. So we're going to sketch the graph of the rational function r of x with the following properties. Okay, so we've got to know how to read limit notation in the end behavior of a rational function. Okay, so if I take a look at this here, as x goes to both negative and positive infinity, the r of x function approaches the y value of 2. These two statements together mean that we have a horizontal asymptote at y equals 2. So as the graph goes to the left and to the right, I have a horizontal asymptote at 2. So I'm going to go ahead and plot that in there. Remember, your asymptotes are dashed or dotted, however you want to say that. All right. The limit as x approaches a value of x from the left and from the right, if it equals a y value, that means that we have a hole. So here, we're going to have a hole. And the hole happens at that x value of 5, whatever that x value is. And because it approaches the y value of 3, that means the y value of the hole is at 3. So at 5, 3, yeah, I'm going to have a little hole there. And then over here, as my function approaches an x value from the left and from the right, and the y coordinates go to positive or negative infinity, that means that I have a vertical asymptote. Okay, and here I have a vertical asymptote at x equals -3, that x value. So I'm going to plot that in here. Gotta make that a little better. There we go. Okay. And then this says x equals 5 is undefined. If you guys look at x equals 5, it's undefined because of the hole. That's where the hole is. Okay. So now, to get other points of this function, you would have to plug in like x values into the actual r of x function to figure that part out. Unfortunately, we don't know that. So, but we can get an idea that this graph kind of goes like this. And more than likely, they'll be opposites of each other when we have that. Unfortunately, we just can't get exact values because we don't have a function to plug in x values to. But usually you will have that. So, yeah, that's it for this problem right here. I think that's everything. Y equals 2, x equals -3. Yep, we are good to go on that problem. Okay.